Hey guys, I'm Pat Kelly. Okay, in this problem, we're supposed to calculate the total work that would be performed by this force on some particle that would be traveling along this path. Okay, they give us this force vector function, but what else I've written for us just to kind of head in the right direction is like the formula for work, which is that force vector dotted with this differential vector in the path direction, the r direction. But a little bit more practical version of that I've also written, I've given us kind of a head start, is that this equals that force vector expressed in terms of t, and then dot that with the derivative of that r vector. And everything's a function of t, if you notice. And so that I definitely hope this version of our work formula looks manageable to you. It should. And if you're looking at it then, that might suggest, hey, everything's in terms of t, those are parameters. We need to get things into parametric representation. And maybe you already thought that way when you saw this old triangle, because you've been doing problems like this. Is what we need to do to start is to come up with a parametric representation of our path. So I'll say r as a vector of t. And because I do have three different sides of a triangle here, it suggests to me that my vector here is going to be piecewise with three different branches. And in that first branch, I'm thinking that t is just going to be my x-coordinate for the I vector. And I won't have a j vector. I could write it for if you want. That's going to be a 0. And I'm thinking that way because the y-coordinate stays at 0, right? And that will be when t is between 0 and 1. Let me slip down then, and I like to kind of focus on my restricted domains here. The next branch should start at 1, and I think it's going to make sense to end it at 2. Maybe I don't know that yet. Do everything in pencil. And so now I'm looking at this hypotenuse of the triangle, and I have to express that in terms of my i's and j's, thinking how the x-coordinate needs to start at 1, but then end at 0. Okay, so that would suggest to me maybe 2 minus t times the I vector. I was trying to line up nice and straight, maybe not so great. My y-coordinate needs to start at 0 and end up at 1. So I think I'd be looking at 1t minus 1 j vector. See if that makes sense. Starts at 0, ends at 1. It looks good. And finally, this last leg, the last branch for my piecewise function, the x is always 0. And my y looks like it wants to be like a 3 minus t times the j. And I forgot to write my restricted domain. I mean, I usually like to start with that, but I knew I was going to pick up at 2 and end at 3 for that. Okay. See if that makes sense. Start at 1, end at 0. This looks good. So my piecewise parametric function for that r vector looks like that. All right, that gives me a push in the right direction for this formula, because now I'm going to know what to have for that r prime vector. And we'll also work with that f vector for each component. Excuse me, so let me come here. Probably going to end up spilling into a lot of different space here, so I'll switch colors to yellow and try to give you a little header here for each of my pieces of work. The C sub 1 is going to be this bottom branch, C sub 2 here, and C sub 3 here. So for C sub 1, I need to find this f function. Let's first get a handle on that. F will equal, and I'm looking at the formula, and that tells me to plug in x of t and y of t into capital F. Capital F is right here. So I'm going to put x in from here, the t. So I just get t, I vector, plus, and then the y, which is your component for the j vector here, which is 0 again. Okay, that's my f. Let's also get a handle on what r prime actually is. I think I can do some differentiation on the fly, if you will. I mean, I see what my R is, and the formula needs R prime, so let's just get a handle on R prime. R prime for that top branch, you're just differentiating component-wise, so the derivative of t is just 1, and you do have your I vector, and 0 is still 0, the j vector. And then I'm ready, let me slip down here, I guess. I'm still working with C1, but I'm ready to find a W value, a work. Let's put it all together. So my work formula is the integral from A to B. My limits here are 0 to 1. Okay. And I would like to do this dot product right now as I enter things into the integral. So I'm looking at F dot R prime, and that's why I have them kind of lined up for myself right now. Remember, your dot product is to multiply corresponding component, so t times 1 is t, and then add the other multiplication, the other pairing of components, 0 times 0, and that's just 0, right? And that's the entire dot product. So I'm done, and I'm ready for dt, okay? First branch wasn't too bad. Let's evaluate this, and this is all still just for C sub 1, but we'll do the same work for C2, C3, and put it all together at the end. This integral is not too bad at all. I'm looking at t squared over 2 from 0 to 1. Put in the top limit, subtract the bottom limit, a half. Okay, now let's try the same type of work for C sub 2. I'd like to first get a handle on F. I'm following my purple formula, but I'm looking in my second branch. So for X, I'm plugging in 2 minus t, and that is all times the I vector, plus, and I'm looking at my Y, which would be my second component there, that t minus 1, and that's times the j. And I'm done with F. See if I can fit it in over here. I would also like to look at my R prime of t for this branch. So my derivative here, derivative is just minus 1, and there is still that I vector. And then plus, the derivative here is just 1, so plus 1 times j. And then you've got your F and you've got your R prime, so you're ready to dot them together within your work integral. So let me go down, get set up for work. Integral from 1 to 2. Let's do that dot product again. If I am multiplying, multiply pairwise, so multiplying this times this, that's just a negative 1 times this. Let me just switch the order of subtraction. I think that's easier. Plus, multiply these two different components, 1 times t minus 1, and that's all dt. Let's see, I think I could go ahead and try to integrate this, because I'll do some combining of like terms in my head. That's looking like a t plus t, which is 2t. When I integrate that, I'll get t squared. These like terms are minus 3, so minus 3t. And I'm integrating from 1 to 2. If I can fit this in, I'm going to plug in my 2 squared is 4, take away 6, looks like minus 2. Subtract what happens when I plug in the 1. 1 minus 3 is a minus 2. Minus 2 minus a minus 2, that's actually equal to 0. All right. Okay, 2 branches down, 1 to go. C sub 3 now then. Let's get our F and R prime ready. My F first is this guy, looking at these components. So I've got 0 times I vector, plus, the plus is actually technically here, plus the 3 minus t times your j. Please don't, there's a convenience, a coincidence here, so please don't look for a pattern. If what I'm writing with my F's look a lot like what's already over here, That's because of the convenience of what my f is in this problem. So you always want to follow this formula. These expressions could be a lot more involved. Squared coefficients, this could have been a subtraction, so focus on the purple for your setup of the f. Okay, I think mine's good. And then r prime for that third branch. So I'm just differentiating, that's a 0 of course, 0i, and then plus, derivative here is just a -1, so minus, I should have put a minus j. I'll just write -1 times j. All I'm really worried about is making sure I can see what I need to see for the dot product, which we'll do now. My w equals the integral from 2 to 3. Now I'm ready to do that dot product. 0 times 0, okay, that's nothing. 3 minus t times that -1. So I'll switch the order again. T minus 3. I think I said that incorrectly before. 3 minus t, I think I did say it correctly. The -1 switches this order. T minus 3. That's dt. Now we're ready to integrate. So I'm looking at a t squared over 2 minus 3t from 2 to 3. All right, and we'll do some arithmetic. 3 squared is 9 halves, minus 9. And I have to subtract what happens when I plug in the 2. 2 squared, 4 over 2 is 2 minus 6. Okay, a little bit of arithmetic. I'm looking for some space for my final answer when I'm ready for it. But 9 is 2 minus 6 minus 4, so add 4, 5. Looks like a minus 1/2. A little bit of arithmetic in my head. Maybe grab a calculator if you want. But I was looking for space because I'm ready for my final answer. I'm going to come here for my final answer. And my overall work then is just the sum of the 3 different paths. We got 1/2, 0, and a minus 1/2. So 1/2 plus 0 plus that minus 1/2. Whew. Easy arithmetic there, I think, is just 0, right? And that's actually intuitive to me, is that your total work is 0 at the end because you started here at the origin and you ended at the origin. Okay, so you did some stuff in between, but the end sum is 0 work there. Okay. All right, hope that helps with some of your other problems, but you've got to go do some of your other problems.